Next presenter is the Professor Sofia with Alisjahbana, Ph.D., Asmi, Ph.D., Safrilah, Jouvan Chandra Pratama, Professor Putra S. Dan Ph.D. and Irene Alisjahbana. They will present the numerical analysis of a Friedlander localized blast load on the right rigid roadway pavement using Levy problem. To Professor Alisjahbana, time is yours.
Okay, thank you very much for the opportunity to present my paper. So the title of the paper is Numerical Analysis of a Friedlander Localized Blast Load on a Rigid Roadway Pavement using Levy's Problem. So this paper actually the result of the joint research done by Bakrie University, Nihon University, and Stanford University. And then on this opportunity, we would like to thank for the Respect Brain for the grant of this research with the number of 087/LL3/PG/2020. My name is Sofia Alisjahbana, and then my co-author is Asmi, Safrilah, Jouvan Chandra, Professor Buntara Esgan, and Irene Alisjahbana is a PhD student at Stanford University. I would like to start with the introduction. The increasing, just a moment, this is okay. The increasing number of terrorist attacks in recent years have shown that in designing structures such as floor slabs and rigid roadway pavement, the effect of blast load should be taken into consideration. In this study, we analyzed the blasting effect on the rigid roadway pavements and provide a numerical example of a toll road shoulder section exposed to this blast load. We assume that the rigid roadway slab is connected by dowels and tie-bars along its edges. Furthermore, we model the blast as a Friedlander blast load, where it is initially a positive pressure before decreasing to a negative pressure due to drag. Blast loading research has gained interest in the last 2 decades, though previous research has focused on empirical methods. Modern computer and finite element methods have facilitated numerical studies in recent years. To further study the behavior of the rigid roadway pavement subjected to a localized Friedlander blast load, this paper presents a comprehensive overview of the dynamic response of rigid roadway slabs subjected to a blast load. The midpoint deflection, the internal shear forces along the edges, and the maximum flexural stress distribution are calculated to provide the essential techniques in increasing the capacity of a rigid roadway slab against explosive effects. Okay, so the next one is a problem formulation. So this is the model of a rigid roadway pavement. In this study, we considered the model of a rigid roadway pavement supported by a 2-parameter soil foundation, or usually it's called the Pasternak foundation model. 2-parameter soil foundation are commonly used to model soil and accounts for shear deformation. Along the edge, we have a double and tie bar. And then this is the equation of motion for a rigid roadway slab is derived based on the elastic thin slabs theory and also from the Newton's second law. And then this is a 4th-order partial differential equation. In this equation, dx is a flexural rigidity in the x direction, b is a torsional, and then dy is the flexural rigidity in the y direction, c is a damping ratio, rho is the mass density of the slab, kf is the stiffness coefficient of the soil underneath the slab, gs is the shear modulus of the soil underneath the slab. Okay. So how are we going to solve the equation of motion? We are going to use the Levy's problem. The Levy's problem consists of two parts. The first one we call the first auxiliary Levy type problem. And then the second one we call the second auxiliary Levy type problem. For the first auxiliary Levy type problem, we are going to solve for the eigenvector in the x direction, and then we are going to use the modified bulletin method. For the first auxiliary Levy type problem, we assume that the spatial function consists of the x function, which is actually this is an eigenvector in the x direction, and then times sine q py over d. Of course, this spatial function has to fulfill the has to satisfy the boundary condition along x equal to 0 and x equal to a. You can see right here, the shear force should be equal to the constants times the deflection. And then the bending moment should be equal to the constants times the rotation. Okay, for the next one, after satisfying the boundary condition along x equal to 0 and x equal to a, finally we find the eigenvector in the x direction that can be expressed by this following equation. We still have a1, a2, a3, and a4. They are all constants that has to be also determined using the boundary condition. The next one is to find the eigenvector in the y direction, and then we are going to use the second auxiliary Levy type problem. The same as in the x direction, in the y direction, the spatial functions should also satisfy the boundary condition along y equal to 0 and y equal to b. And then you can see right here also that the shear force in the y direction should be equal to the constants times the deflection times deflection, okay? And then the bending moment should be equal to the constants times the rotation. Once we got the eigenvector in the x and in the y direction, the next step is to find the p and q. What is p and q? P and q are the number of modes in the x and in the y direction for non-simply supported condition. And then they are calculated from the transcendental equation that satisfies the boundary condition as mentioned before. Once the number of modes P and Q are determined, the natural period of the system can be expressed by this equation. Okay, so now how are we going to solve the total dynamic response of the system? The total dynamic response of the system consists of two parts. The first one is the homogeneous solution, and then the second one is the particular solution. The particular solution can be solved by using the Duhamel integration method. And then you can see right here, there is a dynamic function, dynamic load. So dynamic load will be used in this paper is a Friedlander blast load. So I will explain about the Friedlander blast load on the next slide. So this is the Friedlander blast load. You can see that the Friedlander blast load consists of two phases. The first one is the positive phase. The first positive phase can be expressed by the exponential function, this one, and then the negative phase can be expressed by this equation. Okay. Okay, now we are going to do the numerical example. So this is the data of a rigid roadway pavement. And then on this table, this is this is the coefficient for the Friedlander blast load. Okay, so what is this? So this graph actually shows the time history of the system subjected to the blast load. And then you can see right here, by increasing the duration of TDP or by increasing the duration of the positive phase, you can see that the deflection of the system becomes larger. So actually the duration of the positive phase is really affect the dynamic deflection of the system. I would like also to explain right here that the dynamic deflection occurs not in the negative phase or not in the positive phase, but actually it will occur during the free vibration phase. So you can see here, during the positive phase, this is the response, and then during the negative phase like this, but after the negative phase is over, and then due to the initial condition occur by the end of the negative phase, it will become a free vibration phase with the initial condition determined from the end of the negative phase. So all the maximum response, not only the vertical deflection, but also the bending moment, the shear force, and then the stress distribution also occur during the free vibration phase. Okay, so the next one will be the stress, this one will be the vertical shear force distribution along the x-axis. You can see right here also, by increasing the duration of the TDP, the shear force become larger. So this is for thickness of the plate is equal to 25 centimeter. Next one is the effect of the thickness of a roadway slab. This is actually by increasing the thickness of the slab from 25 centimeter to 26 centimeter and then to 27 centimeter, you can see that maximum vertical deflection will reduce. But by increasing the ratio of TDP over the time period of the system, the response or the maximum vertical deflection will increase. Okay, the same behavior for the flexural stress distribution. By increasing the thickness of the plate from 25 centimeter to 26 centimeter and then to 27 centimeter, you can see the maximum stress will be reduced. This one is effect of the thickness of the roadway slab also. You can see right here that, I explained before, by increasing the duration of TDP from 1.8 millisecond and then 2 millisecond and then 2.2 millisecond, you can see that the maximum flexural stress will increase. The next one is the graph about time history of the system, and then how is the soil stiffness affect the response of the system. You can see by increasing the stiffness of the soil underneath the slab, the dynamic deflection will reduce. Okay, and then this one also, the flexural stress distribution, by increasing the stiffness of the soil underneath the slab, the maximum flexural stress or sigma x will be reduced from 1.4 MPa into 1.2 and then 1.1 megapascal. Okay, and then this is the 3D deflection animation. I only running this for the positive one, but you can see right here the behavior of the system. Okay, you can see right here by the edge of the plate, the deflection is not equal to 0 because the boundary condition is not 0, the deflection at the edge. And then what is the deflection over there that has to be supported by dowel and by the tie bar. So that's why I'm interested about the blast load and then how to design the slab, the diameter of the tie bar and the dowels because of the blast load like this, because there is a deflection between one slab to the other one. And then this one is the moment animation, moment X in the X direction. And then I run for the two phase. The first one is the positive phase, and then the other one is a third phase or the free vibration phases. You can see right here also the moment during the edge is not equal to 0. And then on the free vibration, you can see right here that the bending moment along the edge is not equal to 0 also. Okay. Okay, now we come to the conclusion. Okay, the result of this study can be summarized as follows. The ratio of the duration of the blast loading in the positive phase or TDP over the natural period of the rigid roadway slab or TN determine the development of maximum response for both the forced vibration phases, positive and negative phases, and the free vibration phase. The thickness of the rigid roadway slab greatly affects the overall response of the slabs, including the maximum vertical displacement, vertical shear force, and the distribution of the flexure stress. The thickness of the slab is important to fulfill the technical requirements of the rigid roadway pavement design, and therefore special attention regarding the joint characteristic along the edge of the slab where the dowels and tie bars are located should be given. And then the last one, our results show that the stiffness coefficient of soil underneath the slab has a significant influence on the dynamic response of the slab subjected to a localized blast load. By increasing the stiffness coefficient of the soil beneath the slab, the maximum vertical deflection at the midspan of the slab decreased drastically. However, the rate of decrease depended on the duration of the positive phase of the blast load. Thank you very much for your kind attention.
Yeah, thank you, Professor Sofia. So there is one question from Patria Kusumaningrum. So he said that, good afternoon, Professor Sofia. I'm Patria Kusumaningrum from ITV. So there is three questions from me. The first question is, how do you justify the value you use for spring constant of the soil? The second question, do you apply dynamic increase factor of the materials into your numerical model? And the last one is, have you considered to validate the result obtained from your numerical solution with that of 3D non-linear finite element model, which take into account not only non-linearity of the structure, but also non-linearity of the material, including dynamic increase factor and Fowler surface? Okay, please, Professor Sofia.
Okay, thank you very much. I try to answer the question. Okay, for the first one, actually all the stiffness of the soil, actually we have already compared with the result done by other scientists. I can call, that the paper by Kibigaye. Kibigaye is modeling the soil by using two parameters, and then he also studied how the KF and GS related to the type of soil, for the medium soil, and then for the soft soil, and then for the hard soil. So in this case, I use that parameter for the medium soil condition. So I hope that's answered the first question. And then the second one is, okay, can you repeat again for the second one?
Do you apply the dynamic increase factor of the materials into your numerical model?
Okay. So because this is a numerical analysis, so I didn't put that factor in our analysis. Okay. And then for the third one, I think regarding about the comparing with the finite element result, is that the question?
Have you considered to validate the result?
Okay. So actually, I have validated for the static load by using the strand 7, and then the strand 7 model is done by Professor Buntara in Nihon University, and then that static result has already been validated using the strand 7. And then that's a publication in other journal. I can call right now. Is it in the Journal of Hydro Engineering? So I hope that's answered your question.
Okay. Thank you, Professor Sofia. Maybe from the attendance, there is another question for Professor Sofia. Okay. Thank you, Professor Sofia, for the presentation.